So I'm going to show you what we are doing in Barcelona in relation to the development of some simple devices with interest for diagnostics. And when we say diagnostics, I mean not only health-related diagnostics, but also environmental monitoring, safety and security. And all these with the idea to have cost-efficient devices that can be used everywhere, so as to achieve the so-called democratized diagnostics. So devices that can reach everyone all over the world. So before starting with just a brief description of what I'm going to show you today, first of all, I will speak about, I'll give a brief introduction about my center, about my group, and then about health in general, the point of care devices, environmental monitoring, and then I'll give you some examples of devices we are developing, either optical or electrochemical devices. So I work at Català Institute of Nanoscience and Nanotechnology, as you can see here. This is a joint research center. And this is why you see different logos here, because we belong to different entities, and we are also part of this area I will explain, and we are funded by general regional government, main government of Spain, and also we have as a patron also Autonomous University of Barcelona. And this is where we are. This is the campus of Lateral. Behind this mountain is the city of Barcelona. This is a nice area where the campus of Autonomous University of Barcelona is situated. You can see here different institutes. The green one is our institute. We have next to us also Material Science Institute, Microelectronics, and also we have in the campus a synchrotron. A nice area with around 750 scientists working in the area of materials, micro and nanotechnologies. So our center is really a very multidisciplinary center, trying to work in the frontiers of knowledge at the nanoscale, with the idea, the objective, not only to understand what happened at nanoscale, but also to take advantages of new phenomena and overall to do innovation and technology transfer in this area. Also while training also the next generation of researchers. So we have a lot of interest in developing new materials, techniques, and devices, but also we have a lot of interest in communication and connection with the young generation, and of course their training, training of a new generation of researchers that will work. And in fact, our researchers who have done PhD in our center are all over the world, with a lot of them having leading positions. So, being a multidisciplinary research center, we work in different areas. So we have a lot of interest, as you can see here, not only in health but also in quantum, fundamental basic research in nanotechnology, electronics, energy, environment, of course, beyond. Our research and development goes from manipulation at atomic and molecular scale, so both the top-down and bottom-up approaches, to characterization of nanostructures, fundamental studies, exploitation of functionalities, but also fabrication, design and fabrication of devices based on nanostructures. With around 20 research groups, nowadays we are around 300 researchers working in different areas. As you can see here, we have several groups working in nanoscale manipulation and characterization, nano device fabrication, theory simulation, chemical routes for nanostructures, and also several groups working also with the nano biointerfaces and theories, biosensors, for which together with another colleague, so two groups, we are devoted to the development of biosensors. And as I said, we are also part of Barcelona Institute of Science and Technology. This is why you see us also with this logo, BIST. As you can see, there are 7 research centers, excellent research centers of Catalonia, being ICN2 one of them. This is one of the top research centers in Catalonia and in general in Spain. So at our group, we have as an objective to discover, to develop new devices, but of course, first of all, understanding properties of nanomaterials and trying to find new opportunities, new phenomena that give interest for sensing and biosensing. We have been working since many years with different kinds of nanomaterials, as we mentioned, metallic particles, porous materials, nanopores, carbon nanotubes, graphene, also quantum dots. We have a lot of interest. As I said, in different areas of applications, and also we have interest in technology transfer. I will mention a little bit later, and we have two spin-off companies. One is called Paper Drop, working in diagnostics using paper sensors, and Graphene Lab trying to develop new electronic devices using patterning of graphene with different applications in different areas. As I mentioned, we are trying to get advantages of the nanomaterials. Paper-based sensors are very, very important for us, like, for example, lateral flow. Printing technologies, we work a lot with inkjet printing, but also screen printing, stamping, and also full integration of devices in point-of-care applications, including smartphone-based wearables, wireless readout, with interest for different applications. So, entering now in the topic, so mostly health is one of the most important areas of application for us. But first of all, about the biosensors we are developing, as you know, I'm sure that most of you work with biosensors, so I'll skip this very fast. So this is a very interesting area of research, very with a lot of opportunities, different technologies depending on the receptor, transducer. You may have different kinds of biosensors. So we are working in fact with different receptors and mostly with electrochemical devices, but also with simple optical devices based on paper, like lateral flow. So taking advantages of materials, as you know, materials are very interesting, and they have in the range of sizes up to 100 millimeter. They have simpler sizes with a lot of biological molecules, and this is why one of the reasons why we want these nanomaterials to work together as a building block for new biosensors. Of course, exploring their advantages in terms of surface to volume ratio, but also a lot of physicochemical properties, interesting one that, as you know, are offered by different kinds of nanomaterials. So biosensors nowadays can be everywhere, and not only as medical devices, as I mentioned, but also wearables, smartphones. So everyone has a smartphone and can convert it into a biosensor, but also nowadays everything looks or is standing to be smart TV, smart fridge, smart washing machine, smart houses, food control using biosensors, environmental monitoring, and even smart cities in the future are always requesting the use of sensors and biosensors. In fact, going just to the smartphone, so this is a very interesting area of research in which a lot of research groups, including us, is trying to connect smartphones with biosensors. As you can see here in some examples written several years ago, you can see different possibilities, either the connection of a lateral flow to a smartphone, or converting a smartphone to a microscope, and for applications, including this Google Glass. You see, this guy is trying to use lateral flow. Of course, taking advantages of the technology is reading, quantifying the image, and then transmitting this to the medical doctor or whoever is interested. So this area of sensors overall, not only electrochemical but also optical. For example, this graph for the US biosensor market is going to increase during the years, and you see the tendency and the size of the electrochemical only the sensors. And of course, for these devices to be used as a point of care, they should fulfill also prerequisites to be reassured. Real-time connectivity, easy of specimen collection, affordable, sensitive, specific, user-friendly, rapid and robust, equipment-free, and delivered. To achieve this, we are focused a lot on the use of resting substrates, efficient substrates. We are working mostly with paper and flexible substrates, sustainable plastics. Paper, because nitrocellulose is resting material, it's pliable, low cost, bonded material, easy to manufacture, and also with nice microfluidic properties. So just by capillary forces, you have a running of the liquids. It's a kind of zero energy device. And also we can connect with the great different kind of nanomaterials in paper, transforming paper to plasmonic paper, or even taking advantages of other materials. We are working a lot with conductive beams, nanoparticle-based things for different kind of applications. And imagine all this either with native type, but also simple connection with the smartphone or portable computers is really going a lot in the development of these devices. And in fact, in this area, there are a lot of challenges, as you know. There are different challenges. Sometimes we try to address all of these, or one of them, depending on the application. Either, for example, if you want to divide these devices to be non-invasive, you have to develop different technology. Or if you want to have continuous monitoring, sometimes you need to generate a lot of player data, or in certain application, like for example, in the case of COVID, you need a cheap low-cost device. And of course, depending on the application, sometimes you want these devices for studies of biomedical studies or therapies efficiency. So to see how these data generated by the sensor are correlated to get insight about the body. So this is why we are considering all these materials, nanomaterials, and different without technologies and different substrates. And so far, I've demonstrated some interesting proof of concept applications in different areas. For example, for Alzheimer disease or cancer, some contaminants detection, pollutants, and so on. And here are some examples. I show some of them related to the application of different kinds of nanomaterials. But why do we need fast and efficient diagnostics? Do they say diagnostics not only health, but also environmental monitoring, safety, and security? Just thinking on COVID-19, it was a tremendous example that we are, of course, leaving, but we suffered more than 2 years. And during this time, it was shown that how important is the use of diagnostic devices to be efficient, because this was the first measurement that was taken for us to be protected before medication and so on. So just to consider, and these data are down to the end of 2021, we are living this global crisis that caused 252 million infections and more than 5 million of deaths just in this period of time, and it was more later. So COVID-19 changed in part the scenario, and it showed that developed diagnostic devices, which is a process that is really with several bottlenecks, where different actors should collaborate, not only the scientists, but also the doctor, the regulatory bodies, the companies. And this is why we wrote this review in ACS Nano. It was in the middle of most of the pandemics, speaking about nanodiagnostics, or devices based on nanomaterials, how these can face such kind of pandemics and what are the problems that we couldn't have these devices since the beginning, and still there are problems to solve. And one of the things that we raised there is how you go together the science and business, how you consider the things at this level that are very, very important, since you have the conception of and design of what you're going to do through laboratory testing, clinical trials, regulatory review, scale up and launch of the product. So the collaboration between the research, academia and industry is crucial for such kind of devices to be successful. And all this very, very interesting, and we consider is also with the technologies we're using, we are very much convinced that ubiquitous fabrication of biosensors is very, very important for the future. So we can go from centralized production of nanobiosensors using very, very sophisticated fabrication environment to ubiquitous fabrication of nanobiosensors using simple printers, stamping methods, etc. So based on nanomaterials, things, easy protocols, consumer printers that can be used to fabricate advanced nanobiosensors that can be helpful to supply chain interruption and to face this chain interruption and to democratize these technologies that overall, in general, the diagnostics. So the idea is that by using these nanomaterials, easy and simple and easy production protocols, portability devices, sensitive and reproducible device, and of course, if possible, we may go to what we have in the present to the centralized diagnostics, to this democratized diagnostics, where people in the countries can very fast produce their devices for simple, fast thinking of imaging. And of course, in addition to this, boosting research capabilities in other countries is very, very important to achieve this. And this is why, for example, I just mentioned one project where from Barcelona, we are collaborating together with an excellent center in the Czech Republic to help and to transfer our technologies to Albania. And this is a project in which we are trying to combine our expertise and try to transfer these simple stamping, printing technologies in Albania. So let me show you now some of the examples of the devices we are developing, starting first from optical sensors and then some electrochemical sensors. So as you know, optical sensors are various depending on the way how you measure the light, what kind of light you measure, and how you do it. You may have magnetic, Persian, electrochromic, or bioluminescent in addition to other optical sensors. I mentioned just some of those we have been working since several years. So starting with the first example, so lateral flow biosensors, we know this is now well known all over the world because it's the device that everyone has been using to measure for COVID diagnostics, and this is why we wrote during pandemic this nature protocol so as to teach everyone in the world how to build their own lateral flow. And in this tutorial about the design and fabrication of nanoparticle-based lateral flow, we have been showing in details how one can design, let's say, and how you can prepare all the components starting from nanoparticles to bioreceptors, how you can connect this together, how you can make these conjugates ready and then prepare all the membrane, all the pads, and also how you can do the measurements, of course, sampling and reading, which is very important, not only data qualitative detection, but also semi-quantitative using also and quantitative detection using readers or even smartphone. And also the use of different kinds of nanoparticles, because one can use glue nanoparticles, but also you can use carbon nanoparticles, magnetic nanoparticles, quantum dot, up converting nanoparticles, liposomes. There are a lot of possibilities according to expertise of different labs. The possibilities are enormous to use different kinds of materials. In fact, this is just an example. I'll show you here how we design, for example, this nanobiosensors biosensor based on quantum dots. In fact, this is based on photoluminescence, where we use the graphene oxide as quencher of the fluorescence of quantum dots. So this red dot here, for the detection of bacteria. So this is a very interesting and very simple process in which we take advantages of the quenching capability of graphene oxide or the quantum dots, and you can see how simple it is to build these devices. So this video is showing how we detect these devices, how we prepare these devices, and how we prepare for the measurements. So first of all, you select the paper, you introduce quantum dots, in this case, cadmium selenide quantum dots that are spotted onto the paper, and afterwards, after the excitation of this cadmium selenide quantum dots with invisible light, you see the nice photoluminescence coming from these quantum dots. And afterwards, adding the graphene oxide suspension, the quenching of the fluorescence is occurring, and you see how this photoluminescence is quenched. So the light is turned off, and what we do is we correlate this change of the light with the concentration of the bacteria. So this is a very simple process that, of course, after certain optimizations, of course, depending on the receptor, you can detect different kinds of pathogens. So different applications, including, for example, in this case, we detected respiratory hormone-like hormone in cancer cells with cultures by both nanoparticle-based Lateral Bioassay. This is a work we did in collaboration with our partner in Barcelona, Hospital Sant Joan de Déu, which is devoted to cancer. And we offer these devices based on gold nanoparticles and with special receptors for the detection of this hormone. And the idea was to use this device then for some testing of some drugs that colleagues were developing, and we wanted to have a very simple alternative. As you can see here, it had a very nice variation of this concentration of this hormone with the optical density, and of course comparing these results with conventional techniques, we could work nicely in different cultural media, doing some testing that show a nice correlation that improves sensitivity. So during the COVID also, we are focusing developing and evaluating different kinds of activities. In fact, selection and prioritization of biosensors is crucial for the development of a biosensor, and moreover urgent in the case of COVID. During this period of time, our lab group was working. We are trying to send a message to all the actors in the field that how important it is to do the evaluation, the right evaluation of the receptors, and how important it is for the producers, the industries that are producing antibodies to give a full characterization of these receptors, because from the quality of these kind of receptors depend our work, and in case of emergency was depending also the quality of the devices that the people were going to use for the COVID. And this is why we raise the attention to different companies, comparing different antibodies and finding also some uncertainties in terms of the quality and the efficiency of the receptors. Trying to, of course, to do some testing, and even for nuclear protein to see how it was correlating with the test. So moving toward further developments in lateral flow, in addition to the conventional lateral flow, we have been working with the connection of lateral flow, so optical projection with electrophoresis. So, and this is an example in which we connected the lateral flow with some electrodes, as you can see here. So, with electrodes and trying to get advantage of both lateral flow separation and also electrophoretic separation, with interest for heavy metric samples in which it's very difficult to work directly with simple lateral flow. So by using the smartphone, we are able to connect, to read the results, and also to control all the system by using an inverter. And of course, building this electrophoretic cell, we are able to do several separations, as you can see here, some quantum dots of different colors. So the use of this device was really very interesting. We are still working, as you can see here, we are enhancing the separation by applying the voltage. So this is a whole blood during which we are taking advantages of both the electrophoretic and lateral flow separation. We are still working with this, trying to bring this to a next step with much more integration and application in some real clinical samples. You can see here just some responses of the system in blood, whole blood, or in buffer, or you can see the similar calibration curve thanks to the use of electrophoretic separation. So another very interesting and simple approach has been nano paper. So we have been working with this transparent material in which we integrated nanomaterials, either silver, gold, or quantum dots by in situ synthesis of nanoparticles or ex situ. So trying to put nanoparticles on top of this paper. So by using different kinds of compounds, for example, we tested this with cyanide or other compounds. For example, in the case of cyanide, due to the interaction of this compound with gold nanoparticles, corrosion was occurring. So the change of the size of nanoparticles and in turn the plasmonic of particles was changing. So we found a nice correlation between the color of the paper with the concentration. As you can see here, for example, also different kind of particles showing different kind of color. And here also you can see the paper, which is the most transparent in front of the windows of our institute, and the paper with different color depending on either silver or golden particles. So this was very interesting. We moved this toward the selective detection by combining this paper with antibodies and trying to do the quenching of quantum dot negativity in the paper with graphene oxide. So we have a kind of turned off detection approach that was working fine for different kinds of pathogens, but also even for different kinds of proteins. So a very simple approach for the detection, fast screening of different compounds. We found this, for example, for bacteria, but also it's proof of concept for human NGG, where we show a very nice correlation. We have also a lot of interest in integration. This is why we work also in integrating the system. This is an example of a low-cost, user-friendly, all-integrated smartphone-based microplate, so as to achieve a kind of ELISA in your hand, connected this with a smartphone. So these are the different components. We were able to put not only the temperature control module, but also stepper motor for the ELISA plate, use model, all the components, that's necessary for different kinds of detection because we are using the different kind of particles of different colors. So you can see we were able to do to demonstrate in this simple platform different kinds of interesting applications. For example, colorimetric ELISA for COVID-19, but also bioluminescent measurements or to the measurements with regards for some antibiotic resistance. So these are conventional protocols, but we wanted to show that this device was able to do this kind of measurements and simple connection with the smartphone were able to do reading and, of course, transmission of the signal according to the application, including a simple app that was controlling all the device for different applications. We are extending now these to different other applications and trying to cooperate with industries for commercialization. So all this work we are doing with paper-based sensors are now under development by our spin-off company. So Paper Drop Diagnostics, which is a small medium enterprise that was founded in 2016 here in the same campus. So this is where our spin-off company is in cooperation also with different other centers and hospitals. This company is developing a rapid diagnostic test based on paper microfluidics, of course, trying to be equipment-free, with ultra sensitivity, using different kind of innovative materials, of course, low cost, fast and easy to use, using adaptive platforms, using antibodies, timers, but also using some proprietary technologies, nanomaterials with strong plasmonics, and also developing some new image support and connectivity applications with smartphone. Finally, let me spend the last part of my talk with some electrochemical sensors we have been developing. So, as you know, also this is a very interesting field of research. Technology. You may have different kinds of electrical sensors, just to mention some of them, like ampermetric sensors or potentiometric, depending on what kind of signal you measure, conductometric, metric. You may have also field effect resistors. So we have been working with different technologies, but also different kinds of materials. This is one of them that I will explain. So the stamping of graphene onto different kinds of materials. So we are able to stamp graphene onto paper and develop different kinds of devices, but also including electrocatalytic devices. I'm not going to speak about this today, but only for graphene-based sensors and some improved one using laser scanning. So this is one of the first examples of electrochemical sensors we have been working. This was for Alzheimer disease biomarker detection in human samples. Also again a collaboration with the hospital in Barcelona, in which we used some polymeric particles that were modified with antibodies against the biomarker that we wanted to detect, the biomarker that was in this case for Alzheimer disease, and of course a secondary antibody that was modified with golden particles. By using hydrogen evolution reaction used by gold nanoparticles and using a magnetoelectrode, we were able to measure this hydrogen evolution reaction and quantify the current produced during this process and correlate this current with the quantity of gold nanoparticles that return related to the quantity of the biomarker we want to detect. You see the images of the particles we use as support for the antibodies, and then those that are decorated now with gold nanoparticles during the sandwich formation, and more data that show the correlation of the results, and of course microscopic images and evidences of the presence of these particles. And some data showing the response of the sensors toward increasing concentration of this biomarker for different kind of biomarkers. So moving toward much more sensitive detection approaches, we also reported an electrochemical optimal-based sensor for the rapid and regentless quantitative measurements of SARS-CoV-2 spike protein. For this, we use gold nanowires that were modified with an aptamer that was doing platinum blue as a redox reporter. You know that the interaction of this aptamer, in this case, it was specific to RBD or S protein. We wanted to detect the conformation of the sensor was changing. So over the recognition of the protein S protein, in this case, the distance between the redox reporter and the electrode was changing. So increasing the electronic transference, and we were able to measure this change of the signal during the changes of the protein. So this was a very sensitive approach applied for COVID-19. And also we moved toward much more sophisticated approaches. So in this case, we used we call it electroprogrammable and chemical shaped maybe sample sensor. And this was for single-step detection of antibodies in even untreated biological fluids. This was a very interesting approach in which, thanks to the DNA architecture, we were able to design this DNA that was self-assembling according and then interacting in a very selective mode with the target antibody, as you can see here, using the same operational principle as the one that I explained before, but now using some redox receptors that were connected to the streams of the synthetic antibody. So by using this antibody, in this case as an analyte, we were able to detect very sensitive changes of the current. Of course, these were controlled and also compared with different structures using different variants of the DNA structures, giving different responses that you can modulate according to the analyte you want to detect. The sensor was very sensitive and very fast. In less than 50 minutes, detecting low up to nanomolar concentration, very high specificity. So these approaches we're developing are based, we call these blueprint and play inkjet printing approaches, in which, in this case, this is an example for neutrophil gelatinase associated with cell-in NGAL detection, which is an important biomarker for acute kidney infection and liver cirrhosis detection. So this is in the framework of a project we're working. So the idea is to draw very fast your biosensor on the PC, load your nanomaterial with your consumer printer, print your biosensor, functionalize with aptamer, connect it to your smartphone, and get the result immediately using, in this case, impedance spectroscopy. Of course, the printing of the system is everything using consumer printer, and of course dividing this with wax printer and laser etching to achieve the configuration, the structure of the electrodes we want. In this case, we're using silver nanoparticle-based inks. So starting of graphene is a patented technology where we use filters, paper filters that were with some electrode designed using wax and used for filtering, for example, graphene suspension, or combined with different kinds of particles, and after filtration and pressure, we are able to stamp this. I'll show this later in the video. So we are able to stamp graphene onto different substrates with different configurations with interest for electrical devices, physical sensors, but also for some electrical sensors. So here you can see some of the properties of this stamping technology, where you can see the printing width of the device we are able to do with this simple stamping, and also the kind of devices included, the thickness that we are able to achieve by using this device. And here you can see just a simple touch screen that was stamped with this graphene, showing this turning on off of this LED by touching this surface, which graphene was patterned very, very fast along. So we are able to stamp the graphene to any kind of surface. We are stamping graphene onto PET, paper, textile, adhesive films, and different other surfaces, because we are moving also toward wearable devices. So trying to improve graphene, we are, and this is 2 days ago, out in the publication in Biosensors, we reported this one-step laser nanosuperation of reduced graphene oxide. So we are trying to use laser now to improve this, the quality of these graphene-based electrodes by first reducing the graphene. But the nice thing is that we are simultaneously reducing also some nanoparticles precursors. So we are generating on top of the membranes not only reduced graphene, but also we are generating nanoparticles, as you can see here. For example, we are generating silver, gold, silver, platinum nanoparticles on top of these simultaneously by laser striping, and this is fantastic because this way we have already the surface to be not only electroactively improved, but also ready to unfold the different kinds of receptors that can be used for different kinds of biosensing applications. Here is another example of the wearables we are developing. This is a wearable that is with microfluidics for sweat rate measurement, but also copper detection, which is of interest for several healthcare applications. So all of the electronic is integrated and wireless, in which this sensor is able, thanks to the simple microfluidics, to measure this sweat, and using electrochemical stripping, it's able to detect the copper in the sweat. Here are some details of the device, and also the thickness, so the electrodes, the channels that are incorporated in this device, and more details about the adhesive layers used and where the electrodes are connected for this measurement. And with some typical measurement, for example, showing during impedance, for example, or during electrochemical measurements for different kinds of parameters that we are interested. So either for conductivity, but also for copper concentration using electrochemical stripping, where you can see the different signals obtained using different kinds of procedures. So usually we use electrochemical stripping, but also impedance measurements. So recently, and this is also a few days ago, we also showed that how we can improve these metal detections using electrochemical stripping, thanks to collaboration with our partner in Czech Republic, who supplied us with this metal fluid system. We are able electrochemical system that is used to detect the heavy metals incorporated on top of the electrode. So this metal fluid system that was able to enhance the response to the cadmium and make it possible revealing of this even in presence of high concentration of copper and lead, which is a big problem for the heavy metal detection. Showing, for example, here that in the case of the use of this system modified graphene surface, we have a higher sensitivity in comparison to the bare electrode that does not contain this functional group. So this detection is also has been used by our partners during the field project for water monitoring, in which, in addition to lateral flow that we have been working with for pathogens detection, we applied also heavy metal detection. So trying to connect this with the flow system, as you know. So this was everything integrated in a system that was automatic, and also integrated into a boat, into a boat, in collaboration with our partners, so as to detect directly heavy metals during this operation of this boat in some rivers. So you see here the response of the system for different heavy metals, calibration for cadmium, lead, and copper, simultaneous detection. Also, the use of these in real scenarios, for example, some river here in Barcelona, in Spain, next to some mines that were causing some contamination with some heavy metals. And this was applied also in collaboration with our partners, so both with this boat and with our sensors integrated to measure heavy metals in some rivers. So thanks to this collaboration with our partners in Italy, Greece, but also in California, in addition to the university, the Institut di Verona in Italy. So this is also to finish what our company, the Català, is doing. I'm sorry because the voice is not working. That is explaining better than I do. So how this technology works. So this is really very, very interesting, very simple as we design any kind of paint, any kind of picture. So we can stamp very easy to any kind of surface. So the idea is by using this stamp sensor, we can transfer the sensors to any kind of surface, which is very important because there are a lot of needs for this kind of sensors in different areas, different industries, not only as chemical, biochemical sensors, but also physical sensors. So our technology that combine graphene, the properties of graphene with the properties of other materials is able to bring synergies, very interesting synergies for different kind of applications. So the company is working with this technology, is trying to develop innovative platforms, innovative materials that are based on the combination of graphene and different kind of nanomaterials and receptors, and trying to stamp directly the biosensor to any kind of surface. So this is based on a simple filtering of graphene suspension or composition, composite of graphene with the nanomaterials onto filtering, and then after filtering, transferring this to the surface we want to detect, and then of course building the sensors with interest, including energy applications. We have been collaborating also with some other colleagues using overall simple materials, including textiles, paper, etc. For different applications, as I mentioned, I'm trying to show also here, but also the company is doing other kind of applications with interest for different industries, and of course looking for collaborations also different therapeutic projects and more. So this is a very interesting technology that we're happy that the company is doing fine and looking, of course, for new products and new collaborations. So this is all I wanted to show you. If you need more information, you can read also our reviews. So these are some of the reviews we wrote about heavy metal detection, including pesticides, chemical detection, paper-based sensors, nanochannels, nanomicromotors, and also bio-applications of graphene, and also nanodiagnostic applications. So there are several reviews also during the COVID, as I mentioned, but also how to reach very low detection limits with other analyte sensing techniques, electrochemical sensors or paper-based sensor for cancer diagnostics. And recently we wrote these two important reviews. This chemical review are toward next generation of Lateral Pro, integration of materials. It was last year, and also this year, this 2023 fundamental and applied reviews in optical chemistries. This is the cover of our review toward integrated molecular Lateral diagnostics using micro and nanotechnology. So with all these, I wish that I gave you a flavor about the opportunities that are offered by nanomaterials to build simple devices coupled with, of course, simple platforms paper, plastics for a range of applications with interest for different areas. And of course, I would like to thank all our partners from different parts of the world, and of course, our sponsors who are supporting our research from Spain, but also from Europe and all over the world. And of course, I would like to thank all my collaborators. We are an international team from different countries, almost 50 nationalities now. It's a relatively low picture. So if you want to contact me, you have different ways. And finally, I want to remind you that I wish I met some of you in the Biosensors 2023 in Busan, in Korea, for which I am co-chairman, together with Professor Mango, and also the other conference in my origin country, in Tirana, in Albania, during October 16 and 20, in which, if you can have a look, we have a big panel of speakers with a lot of opportunities, also including the Nanobiosensor School, and also some special sessions dedicated to some important European projects. So a great opportunity to connect with great colleagues all over the world, great professors to bring new projects, new network. So this is all from my side. I'd like to thank you very much, and if you have any question, I'm very happy to give you a response. Thank you very much.